You are given a string S and a list word dict of distinct non-empty strings. Return true if you can split S into one or more dictionary words in order, concatenated with no gaps, so the concatenation equals all of S, otherwise return false. Example 1. S is Leetcode and word dict contains Leet and code. The first 4 letters spell Leet, which is in the dictionary. The remaining letters spell code, also in the dictionary. Together they cover the whole string in order, so the answer is true. We draw depth-first search as a vertical tree of remaining suffixes. Each node is the part of S still left to cover. Branches are valid next segments taken from the dictionary. A cache records pruned or solved outcomes so we do not repeat work. The root is the full string AAB. Every split attempt starts from this node. First branch, try the single letter A as the next block. It is not a whole word in word dict, only double A and B appear, so we prune. We record in the cache that trying a first from here fails. Second branch, the dictionary word double A matches the first 2 letters of AAB. The child node is the leftover suffix, just B. On suffix B, the only dictionary word that matches the front is B itself. We take it and recurse. After consuming B, nothing is left of the string, so this path succeeds. We add to the cache that from suffix B with word B we reach success. That cache is easiest to read with substring-shaped keys, which suffix we are at, and which next segment we tried. That matches how we drew the tree. In real code we store 1 boolean per start index I in the original string instead of copying whole substrings. Suffix B is the same as S from index 2 onward, and the empty remainder is index 3, so the values at 0, 2, and 3 carry the same information as those suffix rows. Solution seen, depth-first search with a per-index cache on Apple Pen Apple. Dictionary words apple and pen live in a set for fast membership checks. We start at index 0 on Apple Pen Apple. To take the first dictionary word apple, we first rule out every proper prefix of that match against the set. The prefix a alone is not a dictionary word, so we prune. Prefix ap is not a dictionary word, prune. Prefix app is not a dictionary word, prune. Prefix appl is still not a dictionary word, prune. Finally apple matches indices 0 through 4, so we recurse to index 5. Similarly, we continue from index 5, extend substrings on the rest of the string, test each fragment against the word set, recurse, and reuse 1 cached boolean per start index until all of S is covered. That cache is true if the suffix from that index can be fully segmented with the dictionary, false if not. We reach index 13, the empty remainder, so the segmentation succeeds and word break returns true. N is the length of S and L is the longest dictionary word. We hash word dict into a set once, then depth-first search with a cached result per start index tries every end index from there, so the dominant work is order n squared times L, and the DP array has n entries, so extra space is order n besides the set. Pseudocode for word break, memoized depth-first search. We store the dictionary in a set once, then at each start index extend the substring to every valid end and test membership. Build a set from the word list so contains checks or constant time. Allocate DP with 1 slot per start index in S, each unset until we store true or false. Start DFS at index 0 with that array. Helper DFS at IDX asks whether the suffix starting at IDX can be segmented. Cache n as the length of S. If IDX equals n we consume the whole string, return true. If dp at idx is already filled, return that cached value. For each end index I from idx through n-1, extend the candidate word. Take the substring from idx through I inclusive as word. If word is in the set and the tail from I+1 breaks, we succeed. Write true into dp at idx and return true. Return true immediately on that success path. If the loop finishes without success, write false into dp at idx. Return false.